So I'm going to be talking about equilibrium in early modern physics. The talk is unfortunately, I think I was overambitious in trying to cram as much as I could in here. So there will be a certain amount of skipping slides. Just be prepared for that. Anyway, okay, so let's get started. So early modern and Enlightenment natural philosophy was really the point of origin for modern thinking about principles of equilibrium. And so one of the most salient aspects of this concept at the time was what's actually integrated into a network of concepts of things like balance, of conservation, of optimality, simplicity, economy, and so on. And they're all kind of vying for a place in natural philosophy by presenting different visions of the perfection of the natural world. And it was really these visions of the perfection of the world that drove the processes of mathematization of nature, as is sometimes said, within a major current, at least one major current in early modern thought. So for that reason, I'm trying to give a kind of reading of equilibrium in connection to attitudes about the mathematical representation of nature in the period. Our attitudes about how it works and why it's possible and why it works so well. And so I'm going to try to highlight one aspect of this that doesn't really fit into standard opinions or perspectives on how mathematization proceeded in this period. So since we're talking about mathematization and nature, Kant is always a respectable place to start. So in the Metaphysical Foundations of Natural Science, he makes this very famous claim. Well, first, he writes that the possibility of determinate natural things cannot be cognized from their mere concepts. It is still required that the intuition corresponding to the concept be given a priori, that is, that the concept be constructed. And this is importantly the task for mathematics. It's mathematics that constructs a concept in a priori intuition for us. And so he makes this very famous claim that in any special doctrine of nature, there can be only as much proper science as there is mathematics therein. Now, of course, for Kant, that meant geometry, really. And, this is this famous doctrine of the transcendental ideality of space. So we can set aside Euclidean geometry in that kind of, and in that role as the a priori form of outer intuition. But this idea of mathematization and the role of geometry was very influential as an interpretation of the scientific revolution. So moving to the 20th century, one of the most important figures this connection was Alexandre Poiré. For Poiré, Poiré kind of followed Kant insofar as he emphasized the importance of the geometrization of physical space. For Poiré, this was basically a Platonist kind of process of identifying physical space with Euclidean space, or what he called the substitution of the concrete space of pre-Galileo physics for the concept of the abstract space of Euclidean geometry. It was this substitution, he writes, that made the invention of the law of inertia possible. So really, he's placing strong emphasis on the role of a certain role for a metaphysical picture in driving the mathematization of nature, namely a Platonist metaphysics, according to which the objects of nature are, as it were, the objects of geometry made real, or something like that. So geometry has an outsized role. And the metaphysical picture is Platonist. And so he actually made a very controversial claim back in the day. He went so far as to suggest that experience or experiment was unimportant to the scientific revolution. He claimed that Galileo's experiments, particularly the ones on free fall, like rolling objects on an inclined plane, he said, yeah, those never happened. Galileo didn't actually do those. He says, it's obvious that the Galileo experiments are completely worthless. The very perfection of their results is a rigorous proof of their incorrection. And so, yeah, I'll leave that there. So now let's look at Eugene. Oh, wait, sorry, wrong Eugene. Eugene Wigner is later in the 20th century, a very famous Nobel Prize-winning physicist, wrote a well-known, widely read paper called On the Unreasonable Effectiveness of Mathematics in the Natural Sciences. And this starts to militate against what we were just saying about the role of geometry. So the first point he says is that he wants to make is that the enormous usefulness of mathematics in the natural sciences is something bordering on the mysterious, and that there is no rational explanation for it. Second, he writes, the principal point, which will have to be recalled later, is that the mathematician could formulate only a handful of interesting theorems without defining concepts beyond those contained in the axioms, and that the concepts outside those contained in the axioms are defined with a view of what he says, what he calls permitting ingenious logical operations, which appeal to our aesthetic sense, both as operations and also in their results of great generality and simplicity. So this is a very interesting set of claims. And what I wanted to observe and what I'm sort of putting it out there for is how significantly in contrast with this kind of standard and very influential picture from the history of science, from the sort of Poiret picture. So a guiding historical question for me is, how did we get to this point? And did it only happen in the 20th century? Did it only happen with quantum mechanics? One last thing I wanted to note. So he writes, whereas it is unquestionably true that the concepts of elementary mathematics and particularly elementary geometry were formulated to describe entities which are directly suggested by the actual world. So there's a kind of clear sense in which the objects of geometry are sort of pictures of objects that we can imagine being in space. The same does not seem to be true of the more advanced concepts, in particular those which play an important role in physics. So we have up here these kind of two influential ideas about early modernity, these historical theses. One being that metaphysics is involved in the mathematization of nature, but it is so in the mode of Platonism. And two, that the effectiveness of math for nature, of mathematics for understanding nature, focuses on geometrization of physical space in the early modern period. So with Wigner's idea as kind of inspiration, there's a kind of ensuing mystery or puzzle, which is that in the early modern period, the obvious thing about what's happening in mathematics is that geometry is progressively being marginalized. And that is happening exactly as mathematics becomes more effective, not less. And so there's a tension with this kind of interpretation up here. So this is a workshop, so I'm taking that we're workshopping it thing very seriously. So here are my working hypotheses. The first is that metaphysics does remain key to understanding mathematization in the early modern period, but it is not by describing entities with geometry, by sort of coming up with pictures of objects in the world and using a kind of Platonist interpretation to regard bodies as the objects of geometry made real or something like that. But by the syntax of the sentence is a little off, sorry. But by the desire for nature to exhibit design. So we have all of these purposive, aesthetic, moral, and economic notions. And so two, this network of purposive or aesthetic ideas is really the focus of efforts to mathematize, because blah blah blah. So these ideas include concepts of equilibrium, balance, harmony, conservation, economy, simplicity, optimality, and so on. And so I'm going to go through some examples shortly. And then finally, that there is, so one thing I'm really interested in is this interplay between metaphysics, mathematics, and physics. And what we see in the period, I think, are a bunch of reciprocal influences between, on the one hand, the sort of formal development of mathematics and metaphysical and physical interpretations. And through this very complex dynamical process that I'm going to try to give a sense of in a minute, the emphasis or the locus of aesthetic emphasis or purposive emphasis shifts from the world as the bearer of these properties of economy, simplicity, optimality, and so on, to the mathematics used to represent the world. And that this is something this is a trend you can see through the early modern period. Okay, so the overall plan. I'm going to give a little bit more background on mathematics and natural philosophy into early modernity. I'll briefly describe Kepler to give a very clear example of Platonist mathematization of astronomy, because Galileo is not as clean of an example. Lots of people disagree with Poiret's reading of him. And then I'm going to talk about the next group of people, Descartes, Fermat, and Leibniz, who are in the latter half of the 17th century, sorry, mid to later part of the 17th century, major figures in this dialectic between kind of mechanical pictures of the world and teleological pictures of the world. And the effort to try to unify these is a kind of important driver to finding more general mathematical principles that apply to nature. And this will also relate to antiquity as well. And then finally conclude with Maupertuis and Euler, who pursue a kind of absolute universality with the principle of least action. Okay. So mathematical treatment of motions and bodies is hard. So early moderns struggled, and it's very natural for them to struggle. Some reigning assumptions that were coming out of the Renaissance when we're asking the question, how do we come up with mathematical treatments of bodies, is that motions are too messy and complicated for mathematics, which is pristine. Motions on the terrestrial plane is the sphere of, violent motions and things like that. They're not susceptible to analysis through mathematics because mathematics, geometry is a pure discipline. Further, natural philosophy is the domain of causes and essences, whereas mathematics does not get at causes. And this is reflected in the kind of method, namely that natural philosophy elucidates causes because it is a deductive discipline based on syllogisms, whereas mathematical proofs are based on diagrams and geometrical arguments. And it was thought, mathematical proofs are often non-unique. They use auxiliary diagrams like we saw with the Archimedes. And so lots of natural philosophers thought, well, these auxiliary diagrams, for example, these are not reflective of things that are actually nature. So how can geometry capture actual natural bodies and their causes? So what spurred mathematization? I'll just kind of quickly go through this. So Poiret thought it was the failures of Aristotelian natural philosophy that motivated a shift towards Neoplatonism. Westphal stresses kind of economic opportunities, a kind of practical explanation. And then Guicciardini focuses on an explosion of kind of translations and commentaries of these classical texts here on Archimedes and others that are specifically focused on statics and fluid equilibrium. So equilibrium is really playing the role of stimulus for this new effort in the early modern period. And it was a kind of a proof of concept that maybe math can apply to nature after all. Okay. So some general observations. So one is that when we start thinking, when moderns start to think once again about principles of equilibrium, an important way into that was through metaphysical principles. Those principles, like things like equilibrium, were actually located in a web of interrelated metaphysical and theological notions. They could not really be considered in isolation, and an important stimulus to research was actually to put them in closer relation derivationally. And finally, the moderns over this period were really feeling their way towards greater mathematical generality by attempting to link together these purposive and aesthetic ideas. So these are just some of them. I've already said some of them: equilibrium, harmony, consonance, conservation, optimality, economy, uniformity, etc. So a couple of points I'll try to illustrate about these. This talk is going to be kind of a historical interpretation. First, that the theory of equilibrium begins increasing in mathematical sophistication once it's plugged into this web of other concepts, these ones on the left here, which have a kind of purposive character or kind of evince design. So they're meant to capture nature, the design of nature, but not by sort of describing entities, by producing pictures of bodies as we might think geometry does. And so the pursuit of a mathematical theory that would kind of package all of these ideas together is something that's driving research throughout early modernity. At least one major tradition in mechanics in the early modern period. And then finally, third, the metaphysical ladder, as it were, is finally kicked out at the end. But it takes almost the entirety of the period, and this probably happens, no sooner than Lagrange at the end of the 18th century. Okay. So what are the dynamics that are going on here that I'm going to try to exhibit by examples? One is that we start with our metaphysical principles like nature is simple or nature is economical or something like this. And then the question is, that's great and all, but what determinate knowledge is expressed by that claim? And increasingly figures are sensitive to this concern and are aware that these metaphysical principles only give determinate understandings of nature once they're mathematized. So to take that principle, nature is simple, simple in what respect, and it's mathematics that's going to tell us what respect. Conversely, physical phenomena or physical bodies, entities, whatever, seem to admit mathematization only when sort of metaphysicalized, as we might say, at least from the perspective of early moderns. And then third, that there's going to be a kind of reciprocal process between physics, empirical evidence, metaphysical understandings, and attempts to subject these representations to ingenious logical operations that gradually puts pressure on and expunges these metaphysical interpretations of them. Okay, I think I've blabbered on enough by preamble. Very quickly, so what I just said was that these concepts up here, equilibrium, harmony, conservation, optimality, and so on, they're both targets of mathematization and instruments of mathematization in the sense that we want to, for example, come up with a quantity that we can assert is conserved in nature and thereby express the constancy or uniformity of nature. But those principles, like conservation of vis viva, for example, would then also become tools for solving problems, for solving particular problems involving particular, they also become instruments of mathematization. Third and fourth, that these concepts all exhibit a kind of purposiveness, this kind of notional association with a set of aesthetic, economic, or moral ideas, but that their interconnectedness, as we'll see, is not only notional, it's not only kind of the vibes, as it were, but early moderns are going to seek to link them together through derivations, through mathematical derivations. These last ones I won't probably stress too much here, but one thing that I think this has in terms of like historiographical implications is that if we really look closely at this picture, traditional categories that we often bring to the study of the early modern period, like rationalism versus empiricism, don't really apply very well. Because we will see metaphysics, physics, and empirical results are all going to be mutually confirming and disconfirming. So I think I'll leave these last two. Okay, so let's look at Kepler. So Kepler, I'm going to go through this very quickly because he's kind of a foil. He's the clearest example of a sort of Platonist approach to what does it mean to mathematize nature? How do you show that mathematics can apply to the world? These are some of his key works. I'm going to talk about a little bit about this last one on the harmony, 5 books on the harmony of the world, where he gives, I don't know if you guys know this, but Kepler had a very, sort of famously like a mystical picture of the structure of the solar system. So he defended a heliocentric model, but he argued for its reality, that it was an accurate representation of the solar system and not just sort of a calculational tool by means of setting up correspondences between, on the one hand, the 5 geometrical solids, 2, the theory of harmony, that is like the theory of musical harmony, and then 3, certain features of the orbits of planets. So basically, what he's going to do, his approach to mathematization of celestial motions is he's going to identify certain orbital parameters that it can represent musical tones so that the solar system can be regarded as a kind of chorus. And then he's going to set that in correspondence with the Platonic solids, as well as 2 that he kind of discovered himself. So the details I'm not going to go into too much, but basically, if you think of an elliptical orbit, just to give a flavor of what's going on here, an elliptical orbit, the orbiting body is going to move at different speeds as it goes throughout this orbit. So as it approaches perihelion, it's going to go faster, and as it goes towards aphelion, it's going to go slower. There's going to be a maximum speed and a minimum speed. And so the key parameter for Kepler is going to be the ratio of the max to the min orbital speed. So for Earth, the ratio is 16/15 approximately. And what Kepler notices is, well, that's roughly a semitone in musical theory. And so he cycles this through all of the planets and thinks that he can find a correspondence sort of map from all of these ratios of the different planets to different tones. And that once you do that, the resulting harmonic arrangement of the planets gives features of this universal harmony. The other feature is the association then in turn with these solids. So basically, his argument is just going to be this pattern could not have happened by chance. And so this confirms this is an explanatory model of the solar system. I'm going to skip through these. So why, for Kepler, does mathematics apply to nature? Well, because God is the universal geometer, the creator, the source of all wisdom, the everlasting approver of order, the eternal and superexistent geyser of geometry and harmony. So that's why mathematics applies to nature. Why this mathematics? His strategy is, or his reasoning is that the more interconnections there are between the kind of musical side, the geometrical side, and the astronomical side, is integrated into a more perfect archetype, and the chance that this happens by chance becomes lower. So it's important that he connects geometry to harmonics and also to astronomy. So I don't know how much to stress these diagrams. I'm trying to map out the relations between these things for these different figures. But what you start with is Kepler observed that there's a close correspondence between a collection of mathematical representations, geometrical solids, harmonic modes, and then physical parameters, orbital parameters, these ratios of the orbital speeds. And then he has this metaphysical principle, Platonism, that God is the universal geometer. And so he takes this to provide evidence for his theory of the solar system, which is to say that it is, called the music of the spheres. Which is his metaphysical conclusion that nature exhibits a fundamental harmony or consonance. Okay, so that's Kepler. Now let's look at Descartes. So Descartes, there's lots to say about Descartes. I'm just going to pull out one feature of Descartes. So Descartes did several important things for advancing natural philosophy. He kind of created the idea of a law of nature. This was a new concept, a universal law of nature. And then he listed several that he thought actually applied to the world. And the idea of God's immutability and simplicity is going to be generative for him of these principles. So I'll go through this quickly. Down here, so for example, he says, we understand that God's perfection involves not only his being immutable in himself, but also his operating in a manner that is also utterly constant and immutable. This fact alone makes it most reasonable to think that God likewise always preserves the same quantity of motion and matter. So this is his argument for what he calls the conservation of quantity of motion, which is a sort of prototype of what we would now think of as conservation of momentum. From God's immutability, we can also know the law of inertia. So he divides the law of inertia into two parts. The first part says that each thing, insofar as it's simple and undivided, always remains in the same state and doesn't change. And then the second law is that the state that it continues to move in is a straight line. And again, immutability and simplicity of God is doing the work here. And then finally, he comes up with some rules for collisions. So I'm not going to go through this again, but just this is to observe that the second part of the law is proved from the immutability of the workings of God. So the way that he understands how the impulses and transfers of motion between parts occur is that it's going to be, the change that occurs is going to be the one that preserves God's action or preserves the quantity of motion the most. And so he ironically says, or unexpectedly says, the very fact that creation is in a continual state of change is thus evidence of the immutability of God. So again, I will go through this kind of quickly, but so we have basically a bunch of metaphysical reasoning that, if you go back to your meditations or the beginning of the Principia, starts with the cogito and clear perception. and moves forward through God's immutability to these ideas of constancy and eventually these physical principles over here, where physical principles like the conservation of quantity of motion, now we're talking about, quantities, about mathematics. Okay, so that put on the table conservation, and that put on the table harmony and consonance. The next step is going to be Fermat. So Fermat is, there is actually a classical precursor for this. So we're talking about the rules of geometrical optics, of rectilinear propagation, reflection, and refraction, or what we know as Snell's law. Hero of Alexandria showed that the first two followed from the principle that light will always take the path that has the shortest distance, which was inspiration for Fermat. This is a new approach to trying to mathematize nature, not by trying to frame bodies to describe them in terms of geometry, but a more abstract principle, an optimality principle. The problem is that obviously does not work for refraction, because if the ray is bent, it's not going to be the shortest distance. Fermat's solution is, what if we instead say that, so this principle of the shortest distance was meant to embody the metaphysical principle that nature always acts in the simplest ways, but it doesn't work for everything. So Fermat thought, what if we modify the way that we are mathematizing this principle? What if instead what light is doing is taking the path of least time, or the quickest path? And so using a kind of prototype of differential calculus called the method of adequation, he shows that you can thereby get the Snell law for refraction from this principle. I'll skip over that. So we get this metaphysical principle that nature is simple, that's motivating a physical principle, the principle of least time, which is allowing us to recover the empirical laws of geometrical optics. And this is taken as evidence for this principle, that it is in fact describing nature accurately. This immediately was subjected to metaphysical critique. So this is an exchange that he had with Claire Sellier. The principle, that is the principle of least time, that you take as the basis of your demonstration, that nature always acts in the shortest and simplest ways, is a moral principle and not a physical one. That is to say, physical principles are ones that deal with causes. So he says this is a moral principle, not a physical one. It is not and cannot be the cause of any effect in nature. He adds, the same principle would make nature irresolute. So what he means here is the principle of the simplicity of nature. Because what does that mean? Sometimes nature is simple in that it takes the shortest path. Other times nature is simple in that it takes the quickest path. Who's going to decide, or who will decide and who will pronounce? So the idea of the simplicity of nature is irresolute. And therefore, Claire Sellier, who is a Cartesian, thinks we should just stick with mechanical efficient causation. So now we have, this is the same diagram, but now we have Claire Sellier thinking there are these metaphysical consequences of your physical principle. Nature is subject to a moral principle, and it makes nature indeterminate. And he takes this to militate against the principle, evidentially, because of its metaphysical consequences. Okay, finally, Leibniz. This is kind of the culmination of this part of the story. Let's see. So Leibniz's project is going to be to use basically the principle of sufficient reason, the idea that nothing happens without a reason, why it should be so and not otherwise, to try to connect all of these principles together. So we saw these principles appear separately before. Leibniz is going to start trying to integrate them. So first step, so this is him on talking about Archimedes and the law of the lever, which we saw discussed by Sarah earlier today. So Leibniz, I found it interesting to hear that Archimedes thought this proof was geometrical, because Leibniz very much thinks this proof is not geometrical. And he thinks it's actually an application of the principle of sufficient reason. Go figure. So Archimedes, he writes, in his correspondence with Samuel Clarke, being desirous to proceed from mathematics to natural philosophy, which is significant, that he thinks that there's a step to take. You have to go from one to the other, whereas it seems like Archimedes did not think that there was a transition at all. In any case, Archimedes was obliged to make use of a particular case of the great principle of sufficient reason. He takes it for granted that if there is a balance in which everything is alike on both sides, and if equal weights are hung on the two ends of the balance, the whole will be at rest. That is so because no reason can be given why one side should weigh down rather than the other. So now we have this very classical and authoritative principle of equilibrium, the law of the lever, which just says that balance will be in equilibrium when the weights are inversely proportional to the distances from the fulcrum. And Leibniz is arguing that this is evidence of a metaphysical principle. This is the key metaphysical principle of his philosophy, the principle of sufficient reason. So we have in Leibniz's picture, the general problem is, how do we get mathematics to apply to the natural world? How can we guarantee that this happens? The particular instance we're looking at now is the principle of equilibrium, of static equilibrium. How can we get the theory of magnitudes to tell us what will happen in a physical system, an actual physical system? So for Leibniz, Archimedes is giving an example of how to do this, a very, an authoritative example. The place of the classical Greek authors was very venerated at the time. So Archimedes is showing the way, and how is he showing the way? Well, it's by a metaphysical principle, by applying a special case of the PSR. Okay. So I'm going to kind of skip through this part because it's just an overload of details. But basically, Leibniz also finds a lot of value in Fermat's approach, the principle of least time approach to optics. There's kind of a technical dispute over the physical assumptions involved in this kind of scenario. Briefly, the disagreement is about the speed of propagation of light. So Descartes and people who followed him, believed that light traveled faster in denser media. And you might think that's a little bit counterintuitive. The idea is something like the denser media sort of compacts and focuses the rays of light, allowing it to travel faster through the medium. This is how he's reasoning physically about it. But Fermat, his principle of least time only gets the correct result for refraction if he makes the opposite assumption. And so there's a bit of a controversy about which is right. Leibniz accepts Descartes' physical assumption, but likes Fermat's optimality principle, so he tries a different approach. I'm going to skip through this because it's not super important. He gives many different attempts, one called the most determined path principle. Another approach is the principle of the easiest path or the path of least resistance, but they're just basically different ways of trying to get this to work still. Where importantly, these principles are all consequences of the PSR in Leibniz's picture. But the next piece of the puzzle, so that was optimality principles, stationary principles, and we also talked a little bit about equilibrium. Now look at conservation, and then we'll kind of try and integrate them together. So in a very famous paper that Leibniz wrote in the 1680s, the brief demonstration of a notable error of the Cartesians, Leibniz recalls how Descartes argued in the following way, that the power or the motive force of a body, so the power of a body is what they understood to be a body's capacity for producing effects in the world. And Descartes thought that that was quantity of motion, bulk times speed, or what we would call momentum, but it was not directional for Descartes. And then he makes an argument from the immutability of God to conservation of quantity of motion. Leibniz disagrees with this. He thinks that the power or motive force of a body is vis viva, but he wants to preserve this same argument from immutability to conservation. And so the way he's going to do it is through implicitly defining power through this physical/metaphysical principle. He thinks the power required to lift 4 pounds 1 foot is the same as the power required to lift 1 pound 4 feet. This is his key assumption. And now, armed with that assumption, he's going to do the following sort of thing to confirm. Sorry, I said assumption. He's going to try to confirm this power principle. How is he going to do it? By relating it to principles of equilibrium. So by taking this power principle and showing that he can derive the principles of equilibrium, he thinks he can get a posteriori evidence, as he puts it, for this principle, which he's then going to use to derive metaphysical. The basic strategy is that from antiquity, we know various rules for simple machines, like the law of the lever. If we assume PP, the power principle, we can demonstrate those, and so we get a posteriori evidence for that principle. This is a common strategy that others use to argue for the generality and truth of their principles, as we'll see with Maupertuis shortly. So what's his argument? So this is, maybe we'll look at this argument. It's a little bit curious. So what we're trying to prove is that a lever is in equilibrium when weights are inversely proportional to distance from the fulcrum. So just to pick numbers, let's suppose that the segment BC is twice that of AC, and the weight at B half that of the weight at A. Goes much quicker than Archimedes' proof. So we're going to prove that this is in equilibrium. And the point is just we could choose whatever proportions we want. It's sort of arbitrary. So suppose for reductio that this were not in equilibrium. What that means is that the weights will change position, because to be in equilibrium just means that they're not going to change position. So without loss of generality, let's just pick some numbers to fix ideas. Imagine B drops to B prime, such that this segment dB prime is 2 feet. Then A is going to raise to A prime, such that EA prime is 1 foot. And so the power principle, Leibniz says, implies the following statement, that these two changes are equivalent, the change from B to B prime and A to A prime. So nothing is gained, and descent becomes useless. And this is a reductio, he thinks. The idea is just that the cause of the power of the cause that produced this change is equal and opposite in direction as the one that produced this change. And so there is, what exactly he means here, that nothing is gained and descent becomes useless. And so the original configuration must have been in equilibrium. That's his argument anyway. So the upshot, however, is that he thinks that the power principle is therefore confirmed, and so we can use it in further arguments. And so what he's going to do next is use this to prove the conservation of vis viva, or what we would regard as twice the kinetic energy of a body. So the power principle says that the power given to 4 pounds, if we take a 4-pound weight and lift it 1 foot, and if we take a 1-pound weight and lift it 4 feet, the power or force that we have given to these bodies is going to be equivalent. Whatever the power of that cause is going to be equal to its effect. Its effect is going to be measured by what happens once we drop those weights back to their original position. So the effect is that they're going to acquire a certain velocity, right? What velocity? Well, that's going to be given by the Galilean law of freefall. The Galilean law of freefall says the 4-pound weight is going to be given 1 unit of speed, and the 1-pound weight is going to be given 2 units of speed. The 1-pound weight at 4 feet, if you drop it, it will have twice the speed of the 4-pound weight dropped from 1 foot. So power is proportional to a body's bulk and to the square of its speed, not to the speed directly. Okay. So we can skip, I'm going to skip this part, but just that the key part of the evidential argument is just that equilibrium principles are taken and they are implying through this evidential argument a conservation principle, the conservation of vis viva. This is kind of my schematic representation of what's going on here. For the interest of time, I will skip over this, but we can, if you have questions, let me know. Okay, last section, Maupertuis and Euler. So Maupertuis, through a series of papers in the 1740s, along with his colleague Leonhard Euler at the Berlin Academy, are advancing a new approach, a new principle of nature that they're going to try to show captures all of these ideas together. So ideas of equilibrium, ideas of optimality, and ideas of conservation are all going to be folded in together according to their plan. This starts with what Maupertuis calls his law of rest, which is, again, an equilibrium principle. So he asserts that when some system of masses subject to forces, it will be in equilibrium when a quantity he calls the sum of the forces of rest are at a maximum or minimum. The details, again, I'm not concerned so much with the details. We would say the work done by forces under a small virtual displacement of the system. So the system is going to be in equilibrium when those are at a maximum or minimum. So now he thinks that this has established a derivational connection between notions of optimality, maximum or minimum, and equilibrium. Euler, later in 1753, or 1751 rather, he gives the talk, defends provides what he calls a metaphysical demonstration of a general principle of equilibrium. So basically, this is just a generalization of what Maupertuis had just done for a certain class of forces, but he's going to do it with a more general class of forces. So he defines a quantity he calls the effort associated to some system of masses. Could be fluid or flexible or whatever. And again, effort is going to be what we would call the work associated to a small virtual displacement of a system of masses. And he's going to assert that the system is in equilibrium when the total effort is a minimum. And he derives this from the metaphysical axiom that every force acts as much as it can, as he puts it. Okay. Okay, so this is a lot of this kind of information overload. So I'm going to try and wrap up here and draw some lessons. What happened? There we go. The last stage of the argument is the principle of least action. So Maupertuis has been surveying all of this previous work by people like Leibniz and Descartes and Fermat and others. And he has a lot of complaints about them. So I'm just quickly going to note some of them. One of them is that conservation of quantity of motion does not hold universally. In particular, Descartes deduces some false laws of collision from them. Conservation of vis viva, what we would call conservation of kinetic energy, holds only for elastic bodies. And we don't have any reason to think that all bodies in nature are elastic. Both of them are founded on metaphysical principles like the law of continuity that Maupertuis thinks are uncertain. We don't have good reason to think that they hold. And neither extends to cover equilibrium, so they're not general enough. So what's Maupertuis' answer going to be? 4 years later, in 1744, he defends or presents what he calls the principle of least action. So his goal is going to be to unify conservation principles, equilibrium principles, and optimality principles all together in one claim, which is this right here. When some change occurs in nature, the quantity of action necessary for that change is possible. So he thinks that this applies to collision and also rest or equilibrium. What's his procedure here? Well, he's basically starting with a metaphysical principle that he takes to be justified theologically, that nature carries out its processes in the simplest way possible. The way he's going to understand simplest is most economical, or as it were, the cheapest. So he needs to identify a quantity that measures nature's sort of cost of doing business, as he calls it. And it's going to be this one here, which is the quantity of action, the integral of the mass of a body times its velocity over the path that it takes. And so he asserts that this quantity of action is the true expense of nature and that which she economizes as much as possible in the movement of light. This fund or this budget, he writes, this quantity of action which nature saves up. The way he's going to mathematize that is by asserting that this quantity is minimized, and so kind of anachronistically, we can say that its variation will be zero, it will be stationary. Why does he think this is true? Well, he thinks it's true because we can use the PLA to derive these things. Again, we return to the law of the lever, an equilibrium principle. He also derives the laws of geometrical optics, as Fermat and Leibniz had tried to do, and he also derives the rules for elastic and inelastic collisions. Euler also has a role in this. I promised I would talk more about Euler, but here we are. In 1744, his Methodes inveniendi lineas curvas rectas, blah, blah, blah. It's a very long Latin title, but basically it's a method of finding curves satisfying a property of maximum or minimum. So this is the first text in what we now call the calculus of variations. The calculus that studies how to find functions that satisfy maximal or minimal principles rather than maxima or minima of specific curves. So he also asserts a least action principle. So here he says that this quantity is minimized. This is a bit of an aside. I'll pass over that for now. So he also uses this to recover equations for free particle uniform motion, motion under gravity, and central forces. So all that is just to say, together, Maupertuis and Euler between them have synthesized a large number of earlier results under this attendant concept of the principle of least action. So they have the laws of optics, collision rules. They've accommodated quantity of motion and vis viva and their conservation, as well as things like projectiles and central force orbits. Why they think this is so great? Well, the whole point was to unify all of these ideas together: conservation, optimality, what am I forgetting? Equilibrium, as well as the kind of the Newtonian tradition in mechanics, which I have been not talking about this talk. The last stage, however, is that equilibrium so far is kind of left out in the cold. They've only got the law of the lever. That's not good enough for Euler. He needs to show the harmony between the general principles of rest and motion of Maupertuis. So Euler takes it upon himself in 1753 to kind of put the last piece in place, which is we have this wonderful principle of least action, this optimality principle that shows that nature is efficient and economical and simple, that also captures conservation, that captures certain principles of equilibrium. And then on the other hand, we have this law of rest, what I noted was a prototype of the principle of virtual work, and he wants to integrate them together. So what he undertakes to do in this paper, and again, I'm passing over the details, is to show that if you assume one, you can derive the other. And so they're mutually implicatory. And so the motive for this research, as he writes here, is to show this beautiful harmony, which seems to me all the more important to bring it more fully to light. And so one will easily agree that the more these two principles are united, the more they will be in conformity with the simplicity of nature. Okay, so to return to the themes from the beginning, from Wigner, we saw that it was the elementary concepts of elementary mathematical concepts that were formulated to describe entities directly suggested by the actual world. But it's through the principle of least action, we now have the unification of dynamical and static equilibrium principles, but this does not seem to be the process here. We're not trying to formulate mathematical expressions that describe entities that are, as it were, pictures of entities. What we're doing is identifying mathematical concepts that are formulated to describe features suggested by our ideal of the world, our ideals of the world as simple, economical, balanced, uniform, etc. Again, alighting a bunch of details, I have a paper explaining kind of what happened with the principle of least action that explains this in more detail. But basically, this is where the metaphysical approach to mathematizing nature starts to crumble. So Maupertuis and Euler, they offer the principle of least action as the way to unify all of these aesthetic and purposive concepts in the study of nature. But what happens is, in attempting to make the formalism represent these concepts accurately, the machinery starts to break down. So here are just some of the problems. One is that the principle of least action, it was discovered that it does not actually prove the conservation of vis viva, it requires it as an extra assumption. It was gradually appreciated that understanding action as nature's expense was not really supportable mathematically. It was understood that it's not always minimized. It is sometimes maximized or sometimes at other stationary points. And it's unclear how this interpretation survives the application to equilibrium, because that case of equilibrium, we're talking about virtual displacements. So we're not talking even about any real motions. We're not talking about change. So how can Maupertuis's principle about which is a principle of change applied to equilibrium? So all of these kinds of issues are emerging about this principle. Okay. All right. So I know this was a very long journey. This is a very long story, but just to, so now I'll be able to wrap up here. So well into the 18th century, my first observation is that Maupertuis and Euler and others are consistently seeking metaphysical grounds for the principle of mathematical physics. Even people like D'Alembert, who are normally skeptical, are not really dismissive of this. But these efforts really start to break down by mid-century with the principle of least action. And that break is finally made a clean break when we get to Lagrange in the Mécanique analytique. So returning to the place where we started with Wigner and Kant and all of them, what we have is a situation where mathematical concepts are no longer designed to describe entities suggested by the world. There is, through this process of trying to force the world to realize our aesthetic ideals of it, that there's a shift in what is bearing our aesthetic appreciation from features of the world, that the world is economical, the world is simple, to features of formal mathematics used to represent the world. But it's a shift that is mediated by or by investment in equilibrium, optimality, and conservation as metaphysically load-bearing properties. And so when we get to Lagrange, where his own version of the calculus of variations is now fully algebraic, now we have Wigner's observation about mathematics being designed with the purpose of permitting ingenious logical operations. This is now moving to center stage. And now we have the situation he identified, that the application of mathematics to the world starts to look miraculous. And so just to conclude, this is William Rowan Hamilton talking about Lagrange, and he's interestingly using many of the same concepts, but now he is not talking about nature as beautiful, as harmonious, as simple, and so on. What he writes is, Lagrange has perhaps done more than any other analyst to give extent and harmony to such deductive researches, by showing that the most varied consequences respecting the motions of systems of bodies may be derived from one radical formula. The beauty of the method so suiting the dignity of the results as to make of his great work a kind of scientific poem. Thank you.
So 20 minutes for Q&A and start with Ray.
Thank you. This was wonderful. I have a really stupid question. So we have people like Leibniz that are talking about conservation of vis viva, but of course it's not conserved. If I throw something in the air, the vis viva decreases, it goes to zero, and then increases. And if I ignore friction, it gets back. Now, what we would now say is, well, look, what's conserved is vis viva plus potential energy, where potential energy difference between two configurations is the amount of work done to go from one to another. And there's a lot of talk about work done from one configuration. So when did people start talking about that? Like start saying what's actually conserved is vis viva plus what we would now call potential energy?
When they first started, I believe that would have been Lagrange, who,
Okay.
in 1788, there was a sequence of developments that started with, I believe it was John Bernoulli around 1700,
Mhm.
who gives an equilibrium principle in terms of what we would now call virtual work. as I noted, Maupertuis and Euler both give versions of this. D'Alembert in his Traité de Dynamique in 1743 is another prototype of this principle. But so the status of the vis viva principle remains controversial throughout this period. Euler and D'Alembert are kind of the ones to point out that conservation of vis viva is just not an absolute principle, and there's not actually any competition between conservation of momentum and vis viva. They're just different properties that characterize different systems under very specific conditions, and they're not universal at all. But as far as I'm aware, Lagrange is the first person to combine those two.
So like if I'm just talking about collisions between two bodies with no external forces acting, then I can say in those circumstances, vis viva and momentum are conserved, right? As long as there's an elastic collision.
Yeah. So I mean, the understanding of what bodily elasticity is or what a hard body is a little bit ambiguous at the period as well. But yeah, so an elastic body would be one understood to be such that there's a deformation, and it is restored to its former shape. So it's a kind of geometrical conception of elasticity. And so under those constraints, vis viva would be conserved. And then the separate case of hard bodies being ones where there's no deformation whatsoever, vis viva would not be conserved, but quantity of motion would be conserved. And so, am I getting at your question at all?
Yeah, I think so. But I mean, what did like if someone's saying vis viva is conserved, what are they saying is happening when they do that? It goes to zero velocity, and then it loses its velocity and then regains it.
Yeah, no, I mean the theory of vis viva is very convoluted in this period because it's also because of the way it is incorporated into Leibniz's metaphysics. Vis viva is a sort of causal power. It's an ability of a body to produce effects in the world, and it is expressly not compatible with relativity of motion either, because it's not. He doesn't have the kind of understanding or the resources to the vis viva is supposed to be an intrinsic property of a body instead of something that can be changed by shifting to different reference frames.
I think I was asking a much more complicated question than I was.
Oh,
so if
okay.
this vis viva is mass times velocity squared,
Yeah.
It's absolutely not conserved if something is thrown up in the air.
Yeah. How would they understand orbits?
No,
Well,
not orbits. Yeah, no.
Well, like as a, yeah,
Literally what I just did.
Yeah.
Like it started out with a certain, and forget about relativity of motion. It started out with a certain velocity, lost it.
Yeah.
And I mean, I think what he has to say is okay. It has because it's higher and because you have to do work to raise it, that vis viva is not just mass times velocity squared, but it includes a certain potentiality to gain velocity.
Yeah.
Which it has more of when it's higher than when it's lower.
Yeah, there's a convoluted economy of interchange between what Leibniz calls living and dead force. And so gravity is going to be a source of dead forces that alter the quantity of living force within the body.
Right. Yeah. So he's already talking about what we would now call calculus.
Yeah.
More questions?
Yeah, thanks, Michael. This is really super interesting. I just wanted to ask you, so a lot of maybe I just missed it, but like you're talking, so a lot of these principles, right? When the way I see a lot of them it's about like justification, like why do certain things move the way they do? It's because God loves simplicity, and then you can you know, kind of formalize simplicity in a certain way, and then and so the early, especially early on, right? And then we get to like, and Leibniz and Maupertuis, they're all ultimately talking about, okay, things move the way they do because God, you know, God, blah 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 blah, right? But then when we get to Hamilton, right, it's like Hamilton's like, well, he doesn't, like, God kind of drops out of the picture and it's all math, right? But then the question is, well, then how do you justify the math that's being used? I mean, how does that transition happen, I guess?
Yeah, I mean, so the thing is, I'm puzzled by this question as well, because when you start towards the beginning of this period, you have a kind of easy answer to that question, why mathematics applies to the world. And then by the time you get to Wigner, you have claims about how, well, it's ultimately mysterious. There's no explanation for it. Because when we're designing systems of mathematical representation of the world or mathematical laws of nature, the only things we really care about are whether they're aesthetically pleasing to us, whether we can carry out clever manipulations and things like that. And so people like Wigner seem content to sort of throw up their hands and like it's kind of a mystery, which to me strikes me as kind of like well, the mysticism has snuck back in through a different route into the understanding of this arrangement. So I don't have, and this is me really trying to start with understanding the shift in attitudes as a historical process. And I'm hopeful that this will, as I look more into it, provide clues to the answer to this question. But I don't know. I think like that's sort of the question that's bothering me is, did we just give up our ability to provide answers to this question?
Yeah, it would be cool to extend it into the 19th century. But
I think so. Yeah, I think that's what I need to do next.
I have a suggestion of an answer to that question. Could you put the quote from Hamilton back up? I love this. So because he says Lagrange has done more than any analyst to give extent and harmony to such deductive researches. So it's not God to put the harmony into it; it's Lagrange who put the harmony. And I'm serious, because I think the reason that Wigner is mystified that beautiful mathematics is applied to the world is because he's forgotten or never knew the history, which is that people took mathematics, which was developed to apply to the world, and put it into a beautiful and elegant form.
So you would retain the idea that the starting elements that Lagrange begins with are more closely connected with elements of reality, and that this is explanatory.
Let's figure this.
I have a possible suggestion for what's going on, is that maybe what's going on is our expectations that our representational resources is changing. And so the trajectory that I saw in this narrative was there was this move from modeling to methods. And that's what becomes prioritized in the latter section here once we reach Hamilton, which is what's the sign that we're doing good science? Well, we have like these tools that we're using, as opposed to in the very beginning, getting the geometry to match up with bodily objects.
Mhm.
So that's one possibility, because I've seen this models to methods dynamic elsewhere. So I'm wondering if that kind of story would fit here. But let's just throw that out there.
I'm just curious, what other, do you have like a case in mind when you talk about models to methods?
I mean, this is like totally far away from, well, maybe not. But we see something.
When you say methods, you mean like mathematical methods?
Yeah.
Okay.
Or this thing of so there's a case I'm thinking about in something like economics, right? Which is like, it's not so much that like a contemporary economist I guess it could, but when I assume something is
at equilibrium, right? It's not so much that the priority is I'm representing the economy that literally is at equilibrium. It's more like I need to bring it down a bit. So the emphasis, why am I representing? Well, so I can. It seems like here saying part of the problem.
Yeah, I mean, I guess the question for me, or that survives that is, I mean, we're talking about Lagrange. I mean, Lagrangians and Lagrange multipliers, economists use them too. But does anyone have like no one, well, I don't know, I don't want to say no one, but at least there's a difference in the degree of success that they have had in physics as opposed to economics. And there does seem to be something that calls out for explanation there. Like, why does it match in the case of physics more so than in economics or something like that? Yeah. Sure. Sure, sure. No, that's helpful. Yeah. Oh.
Our priority.
So who's
This is actually now kind of adding on to what Jennifer said is that sorry, it's complicated. That by 1834, certainly, right? Like you've got Laplace, and all, you know, the major problems of astronomy have been solved. The moon's motion, the Jupiter-Saturn interactions, all of that. And then you've got the development of optics, Hamilton certainly being one of the people who developed it. And so it is this time when like all these fruits of these methods are coming together, and it's like, wow, awesome, incredible, right? So there, I think there is maybe a focus more on the methods, but then there's so um, there's more of a kind of, I can see this switch to kind of a Wigner type way of looking at things, because you got all these successes, but then the question is, well, where's how does that why do the principles we use, where does that success come from? And it becomes kind of a mystery if God drops out of the picture. But then there's the story you could tell about, you know, they come from the empirical, but it is kind of, well, but what's kind of I don't see so much in like people like Hamilton is like a story about the justification for this.
Yeah, I think there is more to it than that. I mean, Lagrange, for example, it's not just that the methods are developing, but they're specifically expunging from the methodology connection to real physical systems. Like the mathematics before Lagrange was all in terms of like coordinates that were supposed to be spatial coordinates, and now in Lagrange you get to generalize coordinates, and so it's not really, we're moving away from a sort of direct representation of the physical world, and yet somehow all of it's not merely that our ability to mathematize nature is preserved, it's even expanded from there.
Yeah, so it's like you don't, like, now they're working with principles, right, that like nobody feels a need to like justify. It's like, oh, Lagrange says this, and then let's see what the consequences are, kind of, right? Anyway.
Okay. But it is still a thing. So I guess in some sense this is a question of how it relates to what I was talking about, but it's a broader point that relates to Wayne's criticism of Wigner and the whole debate here, which is that Yeah, of course, like think like I just the example you just gave, right? Like in Lagrangian mechanics, the generalized coordinates. So why do these guys start doing mechanics and equations of motion in spherical coordinates, right? Well, it's very useful for doing orbital mechanics and when you figure out the shape of the Earth. And then why do they use the potential equation? Well, if you have spherical coordinates and you think about higher order perturbations and trajectories in spherical coordinates, the potential is awesome and it's very tractable. And well, if you have an oblate spheroid, you can disregard the y coordinate. It's perfectly symmetric. There's no rotation going on. So it's like you can also tell this kind of story where like all throughout there are those very particular empirical problems that the mathematical methods are responsive to, right? And I guess like Catherine Breiting and Mary Stan tell like a similar story where you also go abstract, but I think there's this very specific problem in the mechanics of rigid bodies that those guys just can't handle, and D'Alembert and Lagrange they can, right? So I wonder. I guess the question is how do those two stories interact, right? Like the story of the metaphysical justification on the one hand side, but obviously there's a parallel story that at least those actors like would have been aware if you sit Laplace down for a cup of tea, like they would have been aware that they're like addressing very specific empirical problems. So how do those stories interact with each other in the development of those methods? Does that make sense?
How, like the story you were telling about equilibrium and idealization as a
Well,
way
forget
to
about the
identify-
specifics of my talk, but like in general, like those empirical problems that motivate the changes in the mathematics that seem to make it more abstract. Say you go to spherical coordinates from standard Cartesian coordinates, but it like that seems to be more abstract. Or like with Lagrangian mechanics, you have a much more general sense of coordinate. It seems to be more abstract, but it helps solving specific problems, right? Empirical problems, not just like harmony and so on.
Is it also, so what I thought you were saying was also features of the empirical problems that we're trying to solve are things like identifying details that make a difference or something like that.
Yeah, yeah.
Identifying features that are themselves not just sort of capturing a picture of the object, but are themselves abstract features of their behavior or something like that. Like finding what is the word for this, the equipotential surface of the Earth, for example. The thing that you're trying to find that's the target of your empirical research is not itself a thing in the world. It is.
Yeah.
Well,
it's much more flat-footed than this.
I thought it was like this balance between the rotational inertia and.
Yeah, you're completely right about
Okay.
We are trying to figure that out, but my question is more flat-footed. But I feel bad for it's really just about how could these guys not know that of course you can arrange this mathematics beautifully and they ask these metaphysical questions, but they also just solve empirical problems better, right? And how do but I'm gonna let's talk about it in the break. Because there were still further questions that I have here. It's Eugene and then Diana, and then we can have a break and have Wayne's talk. Okay, Eugene.
Thanks for the talk, very cool. Oh, yeah, thanks for the talk, it's very cool. Yeah, I guess my question maybe is related to the wait, I pulled off the wait. Okay, yeah. Yeah, so my question might be related before the discussion before, but I was wondering if there's a way to talk about, make sense of this conceptual, semantic, metaphysical discontinuity of, I guess, equilibrium concepts from the continuity of the equilibrium method. I guess maybe something like this, where there's this method that survives even if the metaphysics doesn't. And I was wondering maybe this gives us reason to think that we got the right method for the wrong reasons. Like maybe for we have some post hoc rationalization of why the equilibrium works so well, but the fact that it works well is a fact, and maybe we can see the continuity by focusing more on the continuity of the method and less on the metaphysical justifications for the method. I was wondering whether you think that kind of story would work out here or not. Yeah.
Yeah, I mean, I think it certainly would. This is like a very, it's a very natural reaction to have, what is preserved in scientific change or what is continuous are the mathematics, the methods or something like that. And that physicists and natural philosophers or whatever will bring all sorts of baggage with them, whether it's metaphysics, metaphysical principles, or whether it's models of lines of force or something like that, and that the process, what is preserved and what is accumulated in science is other stuff which is contingent and incidental with respect to the stuff that's preserved. I guess I'm just trying to explore whether that, like, how seriously we should take that picture, how much we should dismiss the role of, broadly speaking, metaphysical reasoning in why and what motivated, what led these people to formulate the principles that they did formulate. And I'm not necessarily on board with Wigner. I'm not necessarily sure that there is a mystery there, but there is at least some appearance of a mystery there. And if we just give up this idea off from the get-go that metaphysical ways of thinking about nature were at all generative or helpful or contributory to finding the mathematical representations and formalism methods we did, then we have already given up our ability to explain that Wigner type phenomenon. So I don't have any claim to make. It's just sort of a suspicion, and I'm trying to leave it open. That's kind of where I'm at now.
Hi, thanks for the talk. That was really nice. I have a when I saw this quote by Hamilton, I was reminded of a quote that I read in one talk that I gave last year, and it has a kind of a different spirit. So I'm going to read the quote, and then I'm going to ask you to comment. It's a quote by Ponceau. So he says, in the meantime, because our attention in that work, and he's talking about Lagrange's book, was first wholly engrossed with the consideration of its beautiful development of mechanics, which seemed to spring complete from a single formula, we naturally believed that that science was completed, and that it only remained to seek the demonstration of the principle of virtual velocities. But that quest brought back all the difficulties that we had overcome by the principle itself. That law so general, wherein are mingled the vague and unfamiliar ideas of infinitely small movements and of perturbations of equilibrium, only grew obscure upon examination. And the work of Lagrange, supplying nothing clearer than the merit of analysis, we saw plainly that the clouds had appeared lifted from the course of mechanics only because they had, so to speak, been gathered at the very origin of that science. So in view of this, in contrast to that quote by Hamilton and the lesson that you taught us today, and also my interest in the principle of least action is the debate on the meaning of the principle just die. What followed after that? After it was realized that those metaphysical motivations were just not realized, and so what? Yeah.
In effect, yes. In the 1750s, there were a handful of mathematicians associated with the Paris Academy of Sciences, Bertrand, Patrick Darcy, D'Alembert, and others, who were kind of placing this kind of formal pressure on the principle of least action, saying if you really take seriously the mapping that you're trying to set up between the idea of action at the expense of nature and what it actually looks like in implementation, none of it is consistent. And I mean, like, Maupertuis and Euler were kind of the two key defenders of this. Maupertuis, basically, he got sick and died. And Euler, he did kind of move on. The one thing that he tried to do, like, if you look at his letters to a German princess, he tries to give a different kind of approach to the metaphysical underpinning of the principle of least action. And it is related to what I had on one of these slides before about how a force will try to as much as it can or something like that. So he's trying to ground it instead in terms of a least action principle governing like impressed forces and that the least action principle as an integral principle is a consequence of this this like economizing at the scale of the infinitesimal forces or something like that. But that I know Jacobi says something about this in the 19th century, and he just says that this is nonsense, and that's kind of the last reference I have come across to this issue. So okay, one other thing, and then I'll stop, is that by the end of the 19th century, beginning of the 20th century, it gets picked up by Planck, least action principles, but it's as an expression of sort of formal teleology, because he's identifying, you know, variational principles as a mathematical formalism that appears in various different contexts, but there's not really like a physical or metaphysical unity to them all. It's just that wide branches of physics can all be equally formulated in terms of integral principles, and he thinks that there's something significant about it, but it's not metaphysical in this way.